Hello, I'm Carina Kaeser. I'm a master's student at ETH Zurich in robotics, and this work is about how simple soft robots can physically entangle and perform tasks as a group and individually. It's inspired by real California blackworms. So California blackworms is something really peculiar. They can entangle into blobs and move as one, and they can also untangle and move as individuals. Our goal was to design soft robots that can do the same, so tackle collective and individual tasks. Our work introduces a system of pneumatic soft robots that mimic these blackworms, providing a platform to study collective and individual behaviors based on entanglement between agents. So a lot of work in modular and swarm robotics has the goal of units that can get new movement capabilities by linking together. So for example, to be able to cross a gap. In most cases, the individual modules are rigid, and they rely on that rigidity for their collective function. There have been a couple of prior studies with modules that are soft, and these operate in a 2D plane and modules connect at single points of contact. So here we're developing a system of high aspect ratio units, like the worms, and this enables stochastic reconfigurability and decentralized control, allowing adaptation and compensation for single points of failure. So the system works both in air and underwater with both individual and collective locomotion capabilities. Each robot is made out of silicon with an off-center internal air chamber using an open mold dipping method based on the Becker et al.'s work. When pressurized, this asymmetry causes the thinner wall to expand more and the thicker wall to act as a constraint layer, resulting in curling. And we control the movement using a custom pneumatic system with independent channels, enabling different robots to move with varying patterns. So we first examine the locomotion capabilities at the individual level, as this is then the foundation for understanding collective behaviors. So as a biological inspiration, the single blackworms move through peristaltic contractions with the speed tunable through different temperature of the environment. We then characterize the individual robot movement under different pressure actuation patterns, and the robots followed random walk trajectories with displacement per cycle dependent on the actuation patterns. Similar behavior was observed in air experiments, and both the worms and the robots thus demonstrate tunable locomotion, though through different mechanisms. As shown before, the California blackworms form these blobs that are capable of coordinated movement, and this video shows the blob moving in response to food being introduced in the aquarium. And as was found by Özkan et al., the worms perform specialized function within the blob. We then took the same approach in our experiments by designating some robots as entangling agents, while others provided propulsion. And we built these blobs with 3 units, 8 units, and going up to 16 units, that then entangle, move together, and finally disentangle again into single agents. So we measured entanglement strength by pulling apart worm and robot blobs, and in robots the strength increases with higher inflation pressures, and in worms with higher oxygen levels. So both systems show tunable cohesion through environmental and pressure based control. This cohesive strength of the blob can then be used for other tasks such as transport, by forming blobs around objects that both robot and worm collectives can carry items that would be too large for an individual to carry. So these videos show our proof of concept demonstrations with worms transporting a plastic mesh and robots transporting a 3D printed bust. So in this work, we've built a basic proof of concept that replicates the core behaviors of the California blackworms in a soft robotic system. Ongoing work by my lab mate Tobias Geisenberger focuses on embedding the sensors to enable closed-loop control, and looking ahead, we aim to make these robots fully untethered and explore more complex forms of collective behavior, going beyond simple entanglement into dynamic group coordination. Thank you.